Okay, so let's do this question. So we have a snowball that's melting in such a way that its surface area decreases at a rate of 1 centimeter squared per minute. This question is asking to find the rate at which the diameter decreases, and the diameter is 10 centimeters. Okay, so why don't we just talk about some of the things in the sentence and see what's going on. So if this says the surface area decreases at a rate of 1 centimeter squared per minute, um, what should you be thinking about? Like when you develop your derivative and math equation, um, what does this mean? What is surface area decreasing at some rate? What would that imply? Yeah. So this sentence right here, it just means, well, this is the derivative of some function of surface area, and we know this is fixed at a rate of 1 centimeter squared per minute, right? So just based on that sentence alone, we can come to that conclusion. Okay, so how about this one? What is the rate at which the diameter decreases? Um, what? How can you express your ddt for that one? Like, what is this dtt of? This is right there, right? Diameter. So let's say d of t. And then the last clause is when the diameter is 10 meters. Okay, so first of all, we need to know what the surface area, for what type of object. For what type of object do we need to know the surface area for? A sphere, yeah. Anyone know the surface area for a sphere? No, it's okay. It's 4 pi r squared. Okay. All right, so let's put some t's in front of this. So as a function in time, the surface area is 4 pi r of t squared. Okay. Anyone see any potential problems, or can we go straight on to do the derivative? Or you may want to do something first. Not a big deal, but it could be helpful to do before moving. Sure, yeah, we could take out the constant in the derivative. What else can we do? How about the r squared, rt squared? What do we want to find, and what do we have right now? What do we want to find? We want to find the rate at which the diameter decreases, right? But right now we have a function of radius. So how can I write one in terms of the other? Right, I want a d to appear here, right? For diameter. Let's call it diam. so it's too many D's. Yeah, so what is R of t? R of t is precisely, okay, well, twice the radius would be diameter. But if you want to replace radius with diameter, it's 1/2 diameter. Right, I don't want to just multiply by 2r randomly, right? So, but I can have the diameter to get the radius. So that's what we can do. So we have 4 pi d dt of diam t over 2 squared. Okay. So now based on this, we can actually make our life even easier. How can you see that? How else can you simplify this? First of all, everyone understand the step here? Anyway, notice that we have a 2 squared in the denominator. So we can pull that out. And just get pi. Okay. What's the derivative of diam squared? What is this? Yep, 2 diam and then something else, right? Are you forgetting something? One thing you need. It's a chain rule, remember. There's 2 things going on, right? You're doing the diameter and you're doing the square. So I needed a d diam t. Do you see that chain rule? Yeah, it's important. So like the 2 functions are the diameter of t is a function and squared is a function. So that's one why I like to write things of t rather than just saying like, you could just drop everything and just say d squared and then 2d prime or something. But I don't know, I think having it of t really makes you realize that it's a function. So I just recommend that. Okay, so what do we get? We get the derivative of the surface area is equal to 2 pi diameter times the derivative of the diameter. Okay, so now what stuff do we know? Can we fill in some blanks? First of all, what do we want to know, and what do we know? Is there any information that we are missing? Can we plug stuff in? What do you think? Yeah, derivative SA we know. That was our given. Now, I should have been more careful here. It's actually negative, right? Because it's decreasing. So this is -1. Do we know anything else? Because right now, we don't know exactly t is, but we care about the t where, oh, sorry, that's not minutes, it's centimeters. So when diameter is 10 centimeters. So we don't know what that t is, but it doesn't matter. When the diameter is 10. So do that, 10. Is that better? Do you see it's minutes or centimeters? Okay, good. So negative 1 over 20 pi is the derivative of the diameter at t naught. So that's your answer. So, I mean, it depends on what the question is asking, but it might be plus or minus. You know, maybe the rate at which the diameter decreases. When you say decrease, you might already assume negative. So it might be the absolute value of this, but it depends on what the question is asking. But so we can say it's increasing at a rate of negative 1 over 20 pi. But yeah, diameter is 2 times radius. Yeah, so that was our step here. So 1/2 diameter is the radius. That was our substitution there. Okay, yeah. Okay, so any questions on this one? And again, just be careful about the sign there. The wording is always weird. So the rate at which it's decreasing, it might be positive because that's what you're saying is positive, but so it might be absolute value of this. So if you get an answer wrong, you may try the positive. It's a little nuanced. Okay, let's do a different one. Okay, this is similar to one we did last time with a little bit of a difference. We have 2 people that start at the same point. Okay, so that line is just this. Okay, one walks east at 3 miles an hour. Okay, what does that tell you? So that's not east, that's west. So one walks east at 3 miles per hour. And let's call this person person A. So maybe let A be distance between the start, from the start, not between the start, from the start. Okay, what should this tell you? If A is the distance from the start, what derivative do we know? This one, right? dA dt is 3. Okay, so the other walks northeast at 2 miles an hour. Okay, let's call this person B. So dB dt is equal to 2. So the question is, how fast is the distance changing at any point of time? Sorry, after 15 minutes. First of all, how far is A from the start at 15 minutes? Yeah, 3 is the speed, yeah, so 3 times 1/4. So 3/4 miles, right? Because 15 minutes is a fourth of a mile, or of an hour. And then this one, at 15 minutes, B is what? So it's 2 miles an hour, and for 15 minutes is a fourth, so 1/2. So 1/2 miles away from start. Okay, so at any point of time, what is the same between all these states? What is something that you know that's remained fixed? Good, yeah, the angle is 45 degrees, or pi over 4. It's always pi over 4. Right, because it's one is walking east, and one is walking northeast, so that makes a 45-degree angle. Okay, so what do we want to? So what are we trying to find? What, considering this triangle, what is the thing we're trying to find? So a lot of things are changing, and so for what value do we want to? We're looking to change. So let's say it's A, B, or other way around. Yeah, C, but the speed of C, right? So that's this be A1, B1, B2, A2, B3, A3, and yeah, this is C1, C2, C3. So what we want to find is dc dt at 15 minutes. Okay. Any ideas? Wouldn't what? Do we know it's a 45, 45, 90? We know one of the angles is pi over 2, right? Or pi over 4. Do we know it's isosceles? Because they're going at different speeds, right? One is at 3 miles an hour, and one's at 2 miles an hour. Yeah, this looks like maybe a law of cosines. Okay, so what is law of cosines? It's c squared. It's okay. It's a hard one to remember. How remember, it's the Pythagorean theorem with a term taken away. So a squared plus b squared, then minus this junk term, 2ab cosine. Yeah, so since it's not a right triangle, so we can't use any Pythagorean theorem. So the only other choice we have that we know about relating angles and triangles with their sides is either law of sines or law of cosines. So to me, just a good reminder, law of sines. Anyone remember law of sines? I think that's an easier one to remember. Just the ratios are the same. Sine of A over A is equal to sine of B over B is equal to sine of C. Oops, sine of C over C. But we don't have enough information for law of sines. But we know everything for law of cosines, right? We have b, we have a, and we have the missing term, or the angle. So the only thing we don't know and that we want to know is the c term. Okay, so let's do that. Let's do a new page. So we have that c squared is equal to a squared plus b squared minus 2ab cosine. Let's say, we can say capital C. Do like capital C, or should we put theta here? Actually, that won't matter. For what reason? Why doesn't it matter? What is this always? What is big C, or the angle? So this is nice, right? Because yes, the angle is always fixed at pi over 4. Theta is always fixed at pi over 4. So that means this is constant, right? So we don't have to do any derivative of cosine here. So we can rewrite this as c squared. All right, so then cosine pi over 4, yes, is square root 2 over 2. And that's nice, we can cancel out one of the 2's. So we have c squared is equal to a squared plus b squared minus radical 2 ab. Because this 2 and this 2 cancel. Okay, so let's take the derivative. As I write it out, can someone say what the derivative of c squared is? Remember, all these are of t's, right? Because things are changing. What's the derivative of c squared? Oh, there's a squared here. Yep, 2cc prime, 2c of t dc dt. So similarly, 2a of t, a prime of t, dA dt, plus 2b of t, dB dt. And now how do we deal with this one? The last expression? You can say the rule, you don't have to write everything out. Product rule, yeah. So first of all, we can take out this radical 2. And so we'll have dA dt, b of t, plus dB dt, a of t. Okay, so that's a lot. But I think we know some of these things, right? Let's go back. What do we know? What are some things that we know? Yes, we know dA dt, and we know dB dt. So why don't we plug those in? So a is 3 and b is 2. That's 3. This is 2, 3, 2. Okay, so how about at t naught? Do we know anything at t naught? So remember, t naught is 15 minutes. Do we know a and b at 15 minutes? Have it right here. So 1/2 for b and 3/4 for a. Let's remember that. So a is 3/4 and b is 1/2. A is 3/4 and b is 1/2. So this is, I already forgot, 3/4, 1/2, 1/2, 3/4. Okay, so I'll change this color. T naught is equal to 15 minutes. Okay, so why don't we just fill that in? We might need to know one other thing. What other thing do we need to know before we can solve for, what are we trying to solve for again? dc dt, yeah. So what is the last thing we need to do? Yeah, we need to find c of t naught. Okay, did I do those fractions right? Let's see, 3 halves, so 2 times, oh, I forgot a 2 here. Okay, so let's just simplify this. So is that 9 halves, 2, and what's that? 6 halves, which is 3. That's good so far. So 2, c of 15, dc dt. Okay, so last thing we need to know is c of 15. So let's write out that scenario, c of 15. So at 15 minutes, what did we establish about a and b? We established that a was 3/4 and b was 1/2. And we know that the angle is pi over 4. What's c? How do we find c? Yes, law of cosines. Usually when you have to find for a missing variable, you probably need the formula that you use to take the derivative of. Right, so c of t naught squared is equal to a squared plus b squared minus 2a b cosine of the angle. This is a, b, and that's c, big C. Okay, so let's do that. Remember this is squared, so I have to square root it afterwards. So that's, what, 9/16 plus 1/4. So that cancels. We get 3/4 root 2 over 2. Nine 16ths. Might as well start doing common denominators. 4/16, and then 8, so times 2, 6 radical 3 over 16. Squared. So whatever that is, so this is calculator time. So c of t naught is all that. So I don't know if you have a calculator that can do that. 9 plus 4 minus 6 radical 3 over 16. This whole thing is radical 2. Anyway, I'll just leave the rest to you, but we got the main idea. Right? So it's 2 times that stuff, dc dt is equal to 9 plus 4 minus 2 radical 12 radical 2 over 6, or over 2. Okay. Yeah, so then you just solve for dc dt. But I don't want to deal with decimals right now. All right, but did you get the idea? So once So now we have found all the missing pieces. Then we're just able to solve just normal algebra for the missing term dc dt. Okay, so this is a unique one that we had to use law of cosines. So barring any computational errors, this is the way to do it. Questions on this, and anyone need more time looking at it? Okay, so let's do another one. Okay. For the physicists in the room, if you have two resistors with resistances R1 and R2, and they're connected by a parallel, and they give you the formula that the resistance, the total resistance, 1 over R, or 1 over the total resistance, is 1 over R1 plus 1 over R2. So the question is, how much is the total resistance changing when the resistance of the first is 80 ohms and the resistance of the second is 100 ohms? And so the resistance of R1 is increasing at this rate, and the resistance of R2 is increasing at this rate. Okay, so how do we do it? And by the way, I want to use 3/10 because I don't like decimals. 3/10 and 2/10. Okay, so what are my ddt's? What information do I know before even starting? I know some derivatives, right? Yep, we know dr1 dt. This was given as 3/10. We know dr2 dt. This is fixed at 2/10. And when do we care? When R1 is equal to 80 and when R2 is equal to 100. Okay, so how do we, what's our first step after establishing some givens? What do we do now? How do we find how fast the total resistance R is changing? So what do we do? When in doubt, just take the derivative of something, right? So I want to take the derivative of this thing. So d dt of 1 over r of t equals d dt of 1 over r1 of t plus d dt of 1 over r2 dt. Okay, what are some values here? What is the derivative of 1 over r of t? If we know 1, we can just do the rest. How do you solve such a derivative? I need to use some rule. There's two rules you could use. So by the chain rule, if this is r of t to the -1, so by the chain rule, this is a power, negative r of t to the -2. So that's the chain. And then I need to remember one more thing, or not just -1 over r squared, but what else do I need to remember? dr dt. That's the chain. Okay, so since all of these look the same, so it's probably going to be the same for each. So this is going to be -1 over r1 of t squared dr1 dt, and -1 over r2 of t squared dr2 dt. Okay, now what? What do we know? Or at least, what's something we can do to make this nicer? A lot of minus signs there, right? Just multiply both sides by -1. Get rid of all the minuses. So while I'm doing this, someone tell me some info. We know some of this stuff, right? Right up here. dr1 is 3/10. dr2 is 2/10. So just plug that in. And we also know t naught, right? We know some things that's happening at t naught. What do we know at t naught? Oh. Yes, we know that R1 is 80 and R2 is 100. So this is at t naught. So we have dr dt, r of t naught squared, whatever that is. Then 3/10. What was R1 again? It's 80. So 80 squared plus 2/10 over, was that 100 squared? Okay, so the only thing we don't know is r of t naught, right? How do we find r of t naught? So when R1 is 80 and R2 is 100, how do we find R? Yeah, just use the formula. So 1 over R is equal to 1 over 80 plus 1 over 100. So what is that? 100, is that right? Yeah. Oh, I need one more here, right? 8,000. And, oh wait. 10 over 800. That's 1 over 80. And then 8 over 800 is 1 over 100. Okay, cool. This is 1 over r is equal to 18 over 800. So r is equal to 800 over 18. So simplifying that further, you could at least do 400 over 9. And I don't think that divides, unless I'm mistaken. Okay, so that means that this is r of t naught. R of t naught is 400 over 9. Okay, so let's. All right, so this is dr dt over. I'm just going to take the reciprocal. Is 9 over 400 squared. So this is equal to 3/10 times 1 over 80 squared plus 2/10 times 1 over 100 squared. Okay, so solving for dr dt, let's divide. So dr dt is equal to 400 over 9 and times 3/10 and 2/10. Okay, so then multiplying that through and then simplifying it. So whatever that is. Okay, so that's dr dt. Let's see. Yeah, okay, so I only want to do that now, but let's see, we can do 2 times 100 squared times 4 squared over 100 squared. So that can get rid of one of the 100 squareds. And then same thing for here. This is 4 squared times 100 squared. Oh, I can do that, actually, not 100. 40 squared times 10 squared. So that gets rid of the 10s. And then this is 2 squared times 40 squared. So I can get rid of the 40s. And then this is 3 squared squared. Or this is 3 to the 4th. So we can get 10 over 3 cubed times 2 squared. Anyway, I'm doing too much. Okay, anyway, so we did the calculus already, so this is just nonsense fractions. All right, so you get the idea. So we have our formula for the total resistance. So using that, we taking the derivative. So just remembering that we need to take the chain rule whenever we take the derivative of these, because the things that we're taking the derivative are functions of time. So doing the derivative would require chain rule. All right, so any questions on this? So the big steps, again, were finding all the unknowns, right? We need to get to a point where we can actually solve for something. So that was at this point here. So we knew these from the given, and we figured this out by our formula. All right, so any questions? Okay, so we'll finish with related rates. So hopefully you have enough, examples. You get the general idea of how to maybe approach these word problems. So if you get stuck, it's probably because maybe you forgot a formula, or you are misunderstanding the derivative, or misunderstanding the question. How to set up the question. So the more you do these, the more comfortable you'll get. And you'll have practice with that with homework. Okay, so let's move on to linear approximation. So a nice motivation for linear approximation is what we can do is we're going to be able to estimate some irrational numbers. Not all of them, but we can estimate some of them. So let's think about radical 15. So here's the graph y equals radical x. So what we're trying to find is at point 15, let's say this is 15, we're trying to find this y value. What do we know? We know radical 15 is probably close to something, right? What is it close to? What number do you know that's close to radical 15? Yeah, it's close to 4. And why is that? Because we know that 16 is right next door. And that is 4. This is 4. Okay, so how does the derivative play a role? Is that, well, we're going to look at the tangent line. Okay, so let's say we have a curve here, and let's say we have our tangent line here. Now if you zoom in, so remember how the tangent line was created. It was taken from secant lines that connect 2 points on a line, right? If you took these secant lines and brought the two endpoints closer and closer and closer together, this approaches the tangent line. So what's something that you know is that when you're really close to connecting the two dots, right? Would you agree that, well, first of all, this is happening. That these distances between the tangent line and the secant line are decreasing. As you get closer to point in question, the distance between tangent line do you agree with that? And secant line let's say at the point, are decreasing. So we had approached the derivative as decreasing x values, but there's also a sense of decreasing y values. Everyone see that? Yes? No? Okay, I'll assume that's a yes. Okay, so what can we do? Let's do so given a tangent line at x, and let's look at some deviation away from x. Let's use h, because we've been using h before. This point here is f of x, and this point here, oops, this point here is f of x plus h. So this is how we're going to define the approximation. The value between, so this is the difference between a function and tangent line. So this value here on the tangent line, so we may call this the tangent line at x plus h, is an approximation of f of x plus h. So one way to think about it is that the tangent line hugs the curve. So if you're looking at points around a value, the tangent line is a very close approximation of that value. So let's think about it for, let's do radical 17 actually. So let's say this is radical 17. And let's look at the tangent line at this is 17. This value is radical 17. So this is 16, and this value is 4. So the idea what we're going to do is we're going to look at the tangent line at 16, and we're going to say, well, what is the approximation? Actually, let's not use t. I think L is the nice letter. Let's call the tangent line L L of x at 16. So the tangent line. L of 17 is called the linear approximation of radical 17 for the function radical x centered at a is equal to 16. So those are just words, but we'll say why we're choosing 16 in a moment. So first of all, let's find the derivative, or the tangent line. How do you find the tangent line? We can calculate this tangent line. How do you calculate a tangent line? So remember, this is radical x. So this is going back a couple of sections. How do you find the tangent line at a point? You need two things for a line. Yep, you need the slope, and you need a point. So 1 over 2 square root of x, you're saying that's, so I'm assuming that's for the slope. 1 over 2 square root of x is equal to the derivative. So what is the slope? It's a line, right? So it's not going to be a varying slope. So what is the slope of this line? What do you do with that 1 over 2 radical x? You care about a specific point, right? Not just the derivative. At point 16 we care about. Yeah, we plug in 16. So 1 over 2 radical 16, 1 over 2 times 4, 1 over 8. So this slope is 1 over 8. And what's the point? Well, it's exactly 16, 4. So what is the L of x? L of x minus 4 is equal to the slope x minus 16. So we get L of x is equal to 1/8 x. It's minus 2 plus 4. So L of x is equal to 1/8 x plus 2. Everyone agree that's the tangent line? I think so. Okay, so what is the linear approximation? Well, we're saying that the tangent line hugs the curve around 16. Notice that the further out you get, the worse this approximation is, right? So if I plug in like 20, it's not going to be as good as an approximation. Do you see that? Like, this is the actual value, and this is the error, which is more than it is at 17. So as we get further out, like, okay, what if we get down to like, maybe we have to use 16. What happens when we get to like 24? Should we use 16 for our approximation? No, yeah, we have 25 instead. We have one that we know. This is a lot closer. So this is like a better approximation. So this tangent line, that's going to be really close. Yeah, so that's the idea that's what's going on here. Okay, so now let's plug in 17 into here. We get 17 over 8 plus 2. Notice there's no radicals in this expression, right? So I don't need to know what a radical is. That's the whole point, right? We're trying to approximate a radical, so we probably shouldn't use radicals to do that. So what was the nice part about choosing 16? Two things. The point, not that one. The y value is not a radical, and the derivative at the point is not a radical. That's why we chose 16 and not 18. right? If we chose 18, then we get radical 18, but the whole point is that we don't know radicals, so we're approximating. So it's at 25 over 8. Okay, one of you type in 25 over 8, and then one of you type in radical 17. And tell me what you get. Someone do this for me. Then we can take a break. Rad 17, 4.123 dot dot dot. Now 25 over 8. 3.125 dot dot dot. Okay, so not perfect. Oh, did I added wrong, didn't I? Oops. Oh, dear. Yeah. 35. Okay, now type in 35 over 8. So this is a good way to check your work, right? If you don't get something that's correct, something went wrong. 4.375. Okay, that sounds a lot better. Oh. 7, yeah. Sorry. Wow. 33. Can't add today. 4.125. Okay, that's even better. Knew it was really close. Okay, so these are really close. So that really shows it, right? That the linear approximation at 17 is very close to the linear approximation of 1.4 radical 17. Okay, so why don't we take a 5-minute break, meet back at 6:45, and maybe I'll put another practice one out. Cube root of 9. So once you work on that, we'll take a 5-minute break. So let's do this question. So find a good approximation of cube root of 9. All right, what do you think? What function you probably would want to use? Is there a point around that you know? What do you think? What function do you think you should use for the approximation? Yeah, so cube root of 8 is the good number, right? Cube root of 8 is a good number. So what function should you use? Because we need to take a derivative of something, right? So what function? Yeah, cube root of x. So let y equal cube root of x be the function. So just to sketch this, so cube root of 8 kind of looks similar. Let's say it's like that. And what is cube root of 8? Why did you choose 8? Yeah, because cube root of 8 is 2. So 9 is kind of close. So it's a little bit above. So now we're going to look at the tangent line. Since the tangent line really hugs the curve, that this point here, and it's such a good approximation. Oops. Okay, that happened. Well, it's such a good approximation that it's really hard to even distinguish between the 2 points. Okay, so what we're trying to find is L of x, and we can say centered at 8. So this is we need to find the linear approximation of cube root of 9 centered at a equals 8. Okay, so I need a tangent line. So what do I need to do? I need a point and a slope, right? What's my point? Eight comma 2, yeah. 8 comma cube root of 8, 8 comma 2. Now I know there's a formula for all this, but I think this is the most useless formula to memorize because we know how to find tangent lines. Again, and what's the slope? How do you find the slope of a tangent line? I need to find the derivative of cube root of x. And good, I like the x to the 1/3. So what is the derivative? So power, so it's 1/3 x to the negative 2/3. Right, and just a little fraction reminder, 1/3 minus 1 is equal to 1/3 minus 3/3 is equal to negative 2/3. Okay. Okay, so what is your L of x? So I'm just going to move the y1 to the other side. So you agree that's the same thing as what we said before? 8 f of 8 is the point, and f prime of 8 is the slope. Do you agree with that? Answer with a yes. Okay, so that is 2 plus, okay, what happens when you plug in 8 into this? What is cube root? What is, gives it away if I rewrite it. What's 8 to the 2/3? Anyone know? If you don't know, can you express this as a cube root? Oh, are you okay, you're doing cube root. Okay, yeah. So you take cube root of 8 and then square it. Okay, yeah. So you could either do that, cube root of 8 then square it, or you can do 8 squared then cube root it. These are both 4. Cube root of 64 is 4, and then cube root of 8 is 2, and then squared is 4. So this is 3 times 4, x minus 8, and that's the whole point, right? I should have a value that I can actually take the cube root of. So linear approximation is no calculator allowed math, because the whole point is that we don't use a calculator. I'm not mistaken, calculators might actually use linear approximation to, or another form of approximation that's similar to do this stuff. What's 8/12? So divided by 4, 2/3. So 4/3. Is that right? Okay, so this is the linear approximation. Okay, so what do we need to do now? What was the whole point of this question? Was to find an approximation of cube root of 9. So what do we do with this linearization, which they call it? Yeah, plug in 9. So this is, so yeah, so with these questions, like if you need a calculator, you did something wrong. You're not calculating cube root of anything. So this is L of 9, and this is cube root of 9. Okay, so what happens when you plug in L of 9? Uh, 9/12 is, 3 goes into both of them. 3/4 is 4/3. So 9 plus 16 over 12, 25/12. That look right? Okay. So someone put 25/12 in the calculator. Like, you can check your work with the calculator. Oh, it's 2.08. Was that the fraction or the radical? Nice. 2.0833. And what's the radical? Cube root of 9? 2.08008. Oh, that's really close. All right, so it's like only off by order of 1,000, right? That's how that works. So that's really close. By the way, this should make sense. It's close to 2, which is what cube root of 8 is. And it's bigger because cube root of 8 is increasing function. Or cube root of x is increasing. Okay, so questions? Okay. Probably not, no. I just like graphing it because it really shows what's going on, but you probably don't have to graph. So no. Okay, so let's talk about, I want to do one more. Let's do square root of 4.001. So we'll bring decimals, I guess. Okay, how do you approximate this? Yeah, square root of 4 is close. So we should use y equals square root of x for the estimating function. And centered at 4, because it's close. It's the closest perfect square. These integer. Okay, so let's do it. How do you find the linearization? For f prime of 4 x minus 4. So this is 2. Now we need f prime. So it's 1 over 2 radical x. It's 1 over 2 radical 4. 2 plus 1 over 8 x minus 4. And then simplifying it, you get 2 plus 1/8 x minus 1/2. So 1/8 x plus 3/2. Okay, how do you, what's next? Yeah, plug in 4.001. So 4. I don't like 4.001. Why don't we say, oops, eraser. Let's say 4 plus 1/1000th. That's 1,000th, right? Over 8. And plus 3/2. So this is 4,000 over 1,000 over 8. So that's 4,000 over 8,000 plus 3/2. That worked out, right? It's oh, I'm sorry, this is 4,001 over 8,000, right? So it's almost really nice. Oh, I can't erase right now. Okay, so what we can do is express this as 4,000 over 8,000 plus 1 over 8,000. Right, you agree that that's the same thing? Just to make it maybe easier to look at. So it's 2 plus 1 over 8,000. This is 1/2. Whoa. This is 1/2, and plus 3/2 makes 2. Okay, so someone plug in 2 plus 1 over 8,000, and someone plug in 4.001. So that one is 2.000125. Cool. And then what's this one? Oops. 2.000249. That's really close. Right? It's getting, that's really close. All right. All right, so questions on that one. That one's using a decimal instead of the closest integer. Okay. All right, so let's think about some geometry now. Okay, so we're going to use similar, so it's application of linear approximation. And it's actually, when calculus was first founded, this was kind of the idea of the derivative, is that when you change from point to point, for now I will use delta x. So delta x is just some change in x. So for the sake of the calculus, think of it's really small. So this value here is f of x. And then this value here is f of x plus delta x. Okay, so f of x plus delta x. All right, so yeah, so that's x plus delta x. And now if we look at the tangent line at x, then we have some things going on. We have the approximation. So this is L of x. So how do we define that? It was okay, let's say this is A or something. Let's call it A. So it was A f of A, and the slope was f prime of A. Right? So what do you think okay, yeah, so then so this value is going to be delta x, this distance, right? That's x plus delta x. And we're going to find this distance as delta y. So delta y is the change in y corresponding to delta x. So what is that? It's really f of x plus h, or delta x, minus f of x. And that equals delta y. We want to see that geometrically. If this value is f of x, this y value, and this y value is f of x plus h, their difference is delta y. Okay, so let's see how the differential comes into play. Is that what will define this value here? Let's see, so this value is delta y, or dy. Sorry. This value, dy. So we're going to find dy to be the difference between our approximation and f of x. So that's you can think of it as the difference in the tangent line. the change of y in the tangent line. Okay, everyone see that? So the tangent line and the function itself start at the same point. So there's two things going on. There's the actual change of the function, which we'll define as delta y. And then there's a change in the derivative approximation, which we'll define as dy. Everyone see the difference between dy and delta y? So one is the actual change, and one is the estimated change. Or, yeah, the change in the estimation. So change in our estimation. Okay. So what do you think dy divided by dx is? So now this notation is actually meaningful. So we've been using this notation without knowing what it means. But now based on the picture, what do you think dy divided by dx is? Okay, so how about just as the picture? Like, how could you show that in the picture? And why is it the derivative? So why is it the derivative? If you just look at the picture and you take the value dy, that's this distance here, and you divide it by dx, that's this distance here, what value does that give you? So don't even think about calculus. So now you're in algebra. Like what value is this distance divided by this distance? Yeah, it's the slope of this line, which is precisely the derivative. So dy divided by dx is precisely f prime of x, because this is like the rise, and this is like the run. So again, this is, so dy is equal to, you can think of it as f of, let's just use y1 minus y2. Let's see, y2 minus y1. So that's y2. This is y1. And then dx is x2 minus x1. And that's precisely what a slope is. So what does that mean about dy? Dy is precisely the derivative times dx, the change in x. This is called the differential of y. So essentially, it's the derivative attached on with a dx. So it's a product. Right now, we're just understanding. We'll get to questions, but this is the intuition behind it. But this formula is just what you need to know. Okay, so what we can do is okay, so then let's do the same thing for delta y. What do you think delta y would be? So let's just see this picture again. So this is x, f of x, x plus delta x, and this actual point is f of x plus delta x. So delta y is this value, and it's equal to f of x plus delta x minus f of x. That's what delta y is. Okay, so let's do a practice problem. Just give me a moment. Okay, so let's calculate the differential. So calculate differential of y is equal to x squared sine of 2x. Okay, so what is the differential of y? dy is equal to what again? So it was f prime of x dx. So what's f prime? How do you find the derivative of that? I'll keep disconnecting. Oh. Yeah, we need to find the derivative of f, or y prime, or y. So remember, it's this would be product rule, right? Within it, and there's a chain rule as well. So I need the derivative of x squared is 2x, and then times sine 2x, and then plus x squared, and then times the derivative of sine of 2x. So this will be 2 cosine of 2x. That's okay. So this is f prime, and we multiply by dx. So we have dy is equal to 2x sine of 2x plus 2x squared cosine of 2x dx. So this is the slope of the tangent line at a point, right? And this would be the change of x value, and this measures the change of y value in the tangent line. Change of y value via the tangent line. This is the derivative, and this is the change of x value. Okay, so let's do another question. This is kind of more like a word problem. So probably won't finish this one today. Let me get it up. Oops. All right. Okay, so we have the radius of a sphere. Was measured with an error of at most 0.5 centimeters. So using this measurement tool, it was a bit off, maybe. Sorry, not the radius was off, not the whole surface area. So in a sphere, so we take the measurement of a sphere, and at most it was off by 0.05 centimeters. So the question is, what would the error be? What would the max error be? In computing the volume? Okay, so so if you think about it, if you think about it as a function, let's say that this is a volume function. I'm just making something up right now. And let's say at radius is equal to what, 21 is that? That's the actual value. At radius equals 21, it's this value here. But if you perturb it a little bit, like 21.05 or 20.95, then there corresponds a resulting change in the y value. So what does that change? Well, we know change is dx or delta x, right? And then how do you measure? So using the same formula, measuring the error will be some dy or yes, some dy or dy, some dy. Okay, so what we need to do is we need to calculate dy for y, the volume, where dx is our change in radius. I should not use y, because now we're doing something different. dv, where dr is our change in actual radius. Oops. Okay, so what's the volume of the sphere? Remember that one? Yeah, 4/3 pi r cubed. Okay, so so 4/3 of v is equal to 4/3 pi r cubed. And notice that if you change the radius, so for changing radius, the volume is a function of r. So that means we can take the derivative with respect to r. So when we find dv, it will be equal to v prime of r dr. So this is the differential of v. So remember, the differential computes, if we go to our picture again, how far off the error the the distances from the value that we want and the value that we were off by. So if you think about it, this is the error in x, and we measure it by some amount, and then using the derivative, this will be our error in y, where the actual change is always going to be smaller. Okay, so so how do we find the derivative of this? What's v prime? So this is with respect to r, so that's our variable. Yeah, so it'd be 4 pi r squared. Yeah, so 4/3 pi times 3 r squared, and then 3's cancel. So our dv is equal to 4 pi r squared dr. Okay, so using the differential, we know that the maximum error was in the measurement of the radius is 0.05. So our change in the radius is 0.05. And at the point what? It was at the point r equals 21. So again, where was it? Here. So this would be like the point 21. And this is an actual value of the volume if you were to calculate it correctly, but you were off by a little bit. And this would be your error. So somewhere in between here, but at worst, since the derivative is close enough to the curve, the derivative is a good approximation of how bad you went. Okay, so plugging that in is 4 pi 21 squared times 5/100. Okay, so that is 5 pi 21 squared over 25. So pi 21 squared over 5. Okay, so that's the differential in of the volume. So that means that, I don't know, I think it's close to, can someone pull out a calculator? So, and first of all, what's the actual volume? What happens when you plug in 21? V of 21. So someone do 4/3 pi 21 cubed, and then someone plug in pi 21 squared over 5. Oh, sorry, a little over, but we'll just see this. Four-thirds pi 21 squared is 38792.38. And then what's this value here? These won't be close. This is saying how far off you'll be. And what's pi 21 squared over 5? It's not the dv is not an approximation. It's a measure of error. So just in case you think you typed in wrong. $227, okay. So this means that when you take the measurement with this faulty radius, that the value is going to be somewhere between measure between that minus and then that plus. That's a pretty bad error, right? So if you think about like, 277, even worse error. That's pretty bad, right? So if you're trying to measure the volume of a sphere, you should be pretty close in your measurement of radius because, right, 0.05 centimeters is pretty small, right? So if you're off just by, like, let's say if you measured the r equals 21.05, or r is equal to 21, or other way around, 20.95, at most you'll get an error of 227 centimeters cubed in calculating volume. But using the differentials, we can actually kind of discover that. So 227 again is the differential. It's the how far off are we from the value. Okay, anyway, we'll talk more about this next time. I'll see you Thursday. All right, have a good one.